Well, hi everybody. Welcome back to Physics of the Universe. We're still talking about weather. We're still in lesson part 19, which is, we're now at part 6, our 6th video of the unit. This time we're going to be talking about global circulation. What you're looking at in the background with that picture right there, all those little bitty lines that are moving is how the air is moving on the Earth. If you look closely at it, you'll notice that there is some distinct patterns as to how that goes. And those patterns are actually very, very predictable if you know how the atmosphere works. And we have a pretty good understanding of how the atmosphere works already. For example, the first thing that we already know is that at the equator it's hot. And so if the equator is hot, that means that the air at the equator must be rising. And remember, rising air, the air at the equator is hot. Hot air rises, and that creates low pressure. At the poles, the air is cold. So that would be creating high pressure up there. And if you kind of keep that in mind, at the equators it's hot, and in the poles it's cold. Well, this air doesn't just go up off in the outer space. As it gets further away from the surface of the Earth, it gets cooled off. As it cools off, it must go around and come back and head back down towards the poles. At the poles, as that air gets cool, it must hit the surface of the Earth. It doesn't just stop, but it starts to spread out. It oozes like it really is actually like taking syrup and dumping it onto the Earth. And that air hits the Earth and it just kind of spreads out like it would on top of your pancakes. This is called convection. And we can take a lot of those assumptions to where the North Pole, you would generally have high pressure up there, sinking air. At the tropics, we would have low pressure, which would be rising air. So at the equator, if it's warmer, that means warm air rises. And if warm air rises at the equator, so if it's hot at the equator, that means the air must be going up. When the air is going up, it's picking up moisture. As it's picking up moisture, you take warm, moist air, you move it away from the Earth, it starts to cool off, and then it starts to condensate and turn into clouds. Well, if you look at this picture right here, you can see that along this equatorial region through the tropics, there's a whole bunch of clouds. There's a very good reason for that, and the reason is warm, moist air is being lifted and that low pressure and forming clouds. It is very common if you go to the equatorial regions, if you go to countries that are on the equator, you can pretty much guarantee it's going to rain. In fact, I'm going to show you something right here. This is pretty amazing in itself. If you take a look at the biomes of the Earth, remember a biome is kind of like how plants are responding to the dominant climate in the area. So for example, in the tropical areas here, like in northern part of South America, you have the Amazon rainforest. Where's the Amazon rainforest? It's located on the equator. And if it's located on the equator, then it must be raining a lot. Hence, the Amazon rainforest. We go over to Africa. I know a lot of people think of Africa as being either sandy and deserts and stuff like that, or they think of savanna type areas where the lions and the giraffes are. But if you go to the middle of Africa, in this area called the Congo, it is dense jungle. This is where, if you think about the gorillas and the mistar and stuff like that, that is in the Congo. The Congo is a rainforest, much like the Amazon. And if we keep following the equator across, what we're going to find out is that this area right here, the Pacific Islands and the Indian Islands, and even a little bit up into Asia, where India is, Myanmar, Burma, and these places through here, Vietnam, all these places are covered in rainforest. Now, if you lived in India, if you've been to India before, you have something that's called the rainy season or the monsoons. You also get that a little bit in Africa too. And this has something to do with the fact that because this zone right here, this area of low that goes all the way around the globe, it's when the sun is hitting directly on the equator. But remember, I told you guys, when the sun hits directly on the equator, that only happens twice a year. And that low that surrounds the Earth in that area is called the International ITZZ, the International Convergence Zone, International Tropical Convergence Zone. And what that means is that that is the area that's dominated by the lows. It should generally be above the equator. But remember, the Earth is tilted on its axis. So at some points of the year, the Earth is tilted away from the northern hemisphere, is tilted away from the sun, which means the ITZZ will be a little bit below the equator. And during our summer months, that moves up. And if you live in places like India, you have the southern tip is kind of jungly. But you have, as you go up further, a little bit further north, you have what's called the monsoon season. Summertime usually brings the rains. In Africa, these parts of Africa right here, in the summer times, it's usually dry. But in this winter times, summer times it's usually wet. The monsoons come in, but in the wintertime the ITCZ moves away and it becomes dry. So the ITCZ doesn't follow the equator exactly. It kind of moves north and south. So those lows kind of move north and south, but never greater than 23.5 degrees north. So ideally, this is the way it should look. You should have air coming down on the high pressure coming down on the poles, traveling across the surface of the Earth in a straight line, heating up, and then going aloft back to the North Pole. Unfortunately, if you've ever paid attention to weather in Seattle, Seattle would be about right here. That would mean we'd always get our weather from Canada. Wind would generally blow in from Canada. However, we don't get our weather generally from Canada. We get generally our weather from the Pacific Ocean. In fact, the South Pacific Ocean. In other words, it's coming up from the southwest. That air is blowing up like this, not like this. So why does this not work? Well, there's a few reasons for it. First thing is it doesn't move straight. The reason why it doesn't move straight is because the Earth is not standing perfectly still. The Earth is rotating on its axis, and the air is not physically attached to the Earth. It's being kind of dragged by the Earth. And if you think about it, the Earth, if we talk about speed, remember speed is distance over time. If you're at the equator, look how much you have to travel distance-wise, versus at the pole, you don't travel near as much distance. So that distance over the same amount of time affects the speed of how the wind goes. And if you try to go from here to here, you're going to be traveling at a different distance. So think of it like this. You have two trains. These upper latitudes would be the red train, and it's moving slow. These lower latitudes close to the equator is going to be the blue train, and you can see it's moving faster. Now you want to do a trick shot with a soccer ball, and you're going to try to kick the ball into the next net, the train right across you, when you guys are lined up. And you notice it doesn't happen. What happens is the ball curves off to the right. And the reason why is because the blue train is moving so much more faster that it's taking your ball, the ball's traveling with you, and it's curving that ball off to the right. And that's what's going to happen here, is that the momentum is going to carry the wind faster than what it can. And if your wind coming from the north, you're going to be pulled to the left like that. So you're going to always be pulled, to the right, by the rotation of the Earth. So here's your trains again. So this would be your train going faster. The ball should just go directly into the net, but unfortunately it goes off to the right because you're being carried by that momentum. This kind of applies to if you're at the North Pole, you throw a ball to somebody at the equator, it's not going to go straight. It's going to actually kind of curve to that person's left. And by the way, it's a mirror image. Even if you're down here in the South Pole and you do the same thing, it's still going to curve to the left. So it's always being kind of pushed off to the left. And that's what happens with the wind. The wind will be pushed off to the left, depending on which way it's trying to move. Now, if we take a look at this picture right here, this is a picture I just took a couple of minutes ago. So this is actually what's happening on the Earth the day that I filmed this video. And you can see that the air, here it is coming up. And you see it's being pushed off to the left. And up here, coming from the north, it's being curved. It's being pushed off to the left. So what happens is that if you have a system, and this is a low pressure system right here, and it's sucking the air up. As it's sucking the air up, that air is being curved off to the left. This is called the Coriolis effect, and you've probably heard it before described as if you're in the northern hemisphere and you flush the toilet, the water always goes down clockwise. If you flush a toilet in the southern hemisphere, it goes counterclockwise. I'm sorry, I got that backwards. Northern hemisphere counterclockwise, southern hemisphere counterclockwise. That actually doesn't really work in a toilet. You're not going to have a toilet that flushes counterclockwise in the northern hemisphere and clockwise in the southern hemisphere because you're talking about too small of a distance. But when you're talking about larger distance, remember the Earth down here is moving technically faster than the Earth up here. And this is causing the air to be pushed off to the left. Another thing that's a little bit of a problem with saying that the air is going to come from the north and make it all the way to the equators, as it travels across the surface, it's going to get heated up. Or this air at the equator that goes up is going to cool off. It's not going to make it all the way back down to the poles before it starts to sink. So we get what's called convection cells. And depending on what latitude it is, it depends on what's going on. So you got 3 convection cells, and you don't actually need to know this picture, so make sure you study this picture quite well. The first cell you have right here is what's called the Hadley cell. This is where the air is heated up at the equator. It moves away because it can't leave the Earth, so it's got to go somewhere. So it moves to the north and to the south. It spreads out. And then it starts to come back down, and it's coming down. Now, remember, this is low pressure right here, the air going up. Whoops. Back. Over here, the air is coming down, so that would be high pressure. When it comes down, it has to spread out, and it makes its trip back here, or it might go north. Up here at the poles, here you have high pressure, the air is cold, so it's going down, but as it moves across the surface of the Earth, it's touching the surface of the Earth, so it starts to get hotter. When this air is starting to warm up, runs up into this air, they converge. We get this convergence area, and it gets pushed up. So if you're on the surface of the Earth, you're at the equator, the air that comes down to the equator, and you don't feel air coming down, it tends to be still. It feels still. If you're on a ship in the middle of the ocean and you require wind in your sails, you don't want to be caught right here where the air is going up. In fact, they call this the doldrums because it's really dull to have to be there because you can't move anywhere. Your ship gets stuck in this area if it's required wind. The only thing you've got going for you is hoping that the current will push you. However, if you can get a little bit north of that, you can see the air over the surface of the Earth is going to be pushing down. And because it's being pushed down, and because of the Coriolis force, it's going to be pushed this direction to the left. And because it's being pushed to the left, then you're going to have wind over the surface. So between these 2 latitudes, you actually have wind. Here at the horse latitudes, bad story why they call it the horse latitudes, it's the same thing as the doldrums. Here we have high pressure. You don't feel air moving up. In fact, you don't feel air moving. It's just less pressure than usual. And if you're on a ship, that could be a bit of a problem. Once again, you can't move. You're victim to whatever ocean currents there are. And in these cases, you have to make your ship as light as possible. So they had the great idea in Europe to load up these ships to bring to the New World horses. A long time ago, they would load up their ships with horses so that they would have horses in the New World. Well, if you get stuck right here in the horse latitudes and your ship is heavy and you're not moving, and there's some other living creature on your ship that is hungry, what are you going to do? You're probably going to throw it off your ship. So if you have a bunch of horses on your ship and you can't move and you're stuck at the horse latitudes, this is not a good place for horses. This is where they usually would throw horses off of their ship just to get their ship moving. So that's an area of high pressure, air not moving. Then if you get a little bit further north, now the air is returning to the north, and Coriolis effect pushes it this way. So these are called the westerly winds. Winds are always named from the direction they're coming from. So these are coming from the west, blowing towards the east, towards the northeast. These are called the westerly winds. Here we have another area of low. This is called the polar front, and just north of that polar front, you would have the that cool air from the poles moving, and once again being pulled off to the right in the northern hemisphere. That's called the polar easterlies. So here you have the cells. It was called the Hadley cell, the Ferrel cell, and the polar cell. And you have the doldrums, the horse latitudes, the polar front. Then you have the highs, the polar front, which is a low area, so you'd expect a lot of rain. You'd expect this area to be dry in the highs and the horse latitudes and rainy in the doldrums. And mirror image in the south. It's the exact same thing in the south, except it goes a different direction. So if that were true, that means about 30 degrees north latitude generally, you get high pressure, which means the air is sinking. Well, if the air is sinking, you can't have clouds, because if you have a cloud and the air is sinking, the cloud's just going to come down on the earth. No clouds, no rain. So if we go 30 degrees north, what do we see? Well, we see the deserts of northern Mexico and the southwest United States. We see the deserts of the Sahara and the Middle East and Mongolia. The reason why these are all deserts, and we see this in the southern hemisphere too, deserts of the southern parts of South America, the southern parts of Africa, and of course Australia, which is almost nothing but desert. The reason why it's like that is because that area, much like the equator, which was dominated by moisture, this is dominated by high pressure. They don't get clouds. They get a lot of sunlight, and it tends to be very dry. In fact, if we look, this is a biome map. If we look at a biome map, we can actually kind of sort of predict what's going on. At the equator, where it's generally rainy because of the low, you get rainforest. At the 30 degrees north, where it's generally high pressure, you get deserts. If you go up to 60 degrees north, that's where you get that polar front. That is kind of sort of where we live. We live just a little bit south of that. But remember, during the winter months, that 60 degrees north is going to slink down to us. And what's it like in the winter in the Pacific Northwest? Very rainy. We have rainforest. In fact, as we go across the top here, we have tundra, Arctic rainforest and tundra. Same thing in the southern hemisphere, though there at that latitude there's not much land to talk about. But the only place that's really forested is this in Australia, is this really, really southern tip right here, and up here in the almost tropical area in the northern tip. So you can actually look and see on the earth where things are predictable as to where the moisture is going. Which kind of leads me to kind of this other real bizarre thing. American history has everything to do with what we're talking about right now. Early on in American history, you have to remember that when we were trading as a young country, as the original 13 colonies and such, when we were trading with Europe, you couldn't just hop in a boat and go back and forth to Europe. And that was, Europe was the people that were France and England and all those countries in Spain. Those were the areas that were settling the New World. So you couldn't just hop into a boat and go to England and then come right back to North America because, number one, boats didn't have motors. Boats moved by two methods, sail, or they had to follow the current. So it actually would be pretty easy to leave, like, say, New York and travel straight to England because, generally speaking, you would have the westerlies. And remember, the westerlies went to the northwest. The winds generally blew to the northwest. So you would just hop on your boat, and by the way, the wind blows the surface of the ocean. So the wind, those westerly winds, are actually blowing the ocean in this direction as well. So you in your boat with the winds and the ocean current working with you would easily go to Europe. But to go back would be like going upriver. The water is moving against you, the wind is moving against you, you can't do that. The good news is that water, once it hits Europe, it can't go any further because there's land. So the water, and seeing that it has to keep balance, would actually kind of turn around, create a cycle. So the ships would go down, you would start in England and work your way down France and Spain and through Africa. You would follow the currents of the ocean down to Africa. And this is the unfortunate part of our American history, is this: we went to Africa and said, hey, look, what can we trade from here? And they didn't exactly trade, they took people. This is the region in which they were taking the slaves. They would take their goods from England and slaves, and they would catch the trade winds. Remember, those are the winds that were coming from the southwest, and they would follow those winds and the currents and end up in these islands. And if you look at the islands in these areas, places like Jamaica and Haiti, the Caribbean, dominated by people from Africa. These were the first trading points for slaves. Then they would come in, they would either go up the coast, or they would really go into the Gulf of Mexico, land in New Orleans. The reason why New Orleans was so important is that there's a lake. You can go from the Gulf into the lake, park your boat there, trade your slaves and other goods, and then the Mississippi River flowed into the United States. So you would just, it's about 3-4 miles from the Gulf to the Mississippi River, and then you would just ship your goods and slaves up the river. So this is why the South is really known for having its slaves. This is where you brought your slaves and you dropped them off and you sold them. They didn't get them much in the North because you didn't want to have to carry that extra cargo up. So whatever you traded for in the South, you would purchase manufactured goods from the North and then return back to Europe and then do that whole cycle. So the whole trade triangle was based on ships knowing how to use those winds and the ocean currents to move it along, because they didn't have motorized boats at the time. And even today, with motorized boats, you want to get the best gas mileage, I suppose, that you could possibly do. So even motorized boats will still use this pattern as well. All right, that's it for today. Thank you guys for listening. Next time we'll be talking about how we make clouds and the different types of clouds. So thanks a lot and have a good one.